biological weathering is kind of neat because biological weathering can take place either as physical weathering or as chemical weathering. When we think of biological weathering occurring as a physical process, we can see things like roots from trees and even the roots of small weeds getting into a little tiny crack on the pavement will start to then apply pressure to the sides of that sidewalk, or if it's a tree root, in this case with this picture, that root at the tiniest ends of its fibers will find the smallest little avenue and crack, and as the girth of that root expands, just like frost wedging or ice wedging, it applies pressure to the rock and then causes that rock to have a failure and push that rock apart, causing it to crack even further. Animals are amazing weathering agents. I've got a picture of a marmot here digging a burrow, but any animal that digs or wallows, like bison and buffalo with their wallowing, which they rub in the mud and in the dirt, will cause weathering. We can think about animals as using scratching places, birds creating mud nests like wrens and swallows, where they transport mud from one area to another, is a form of weathering. Chemical weathering then is the extraction of minerals that are leached that grow on rocks. So with biological weathering with that, and I've got a picture actually here of Arches National Monument, which is not a biological weathering process. That's created from salt. But in this case, I wanted to show you Arches because it's probably the most quintessential chemical weathering landscape in, if not the world, definitely in the United States. So plants, as I said, are going to add acid to that rock and decay a rock. So that's the chemical mechanism of biological weathering. All right, and lastly, if this slide set talking about geomorphology is mass movement or mass wasting. When we say mass, the geographer and the geomorphologist is talking about a large volume of matter that moves. All right, and this is always pulled down with gravity. So we are moving material from a high location to a low location. There are 4 types of mass wasting: material which falls, material which slides, material which flows, and material which creeps. If you have a condition where the material is wet, so if we're looking at this slide right here, on the y-axis, I've got water, how much moisture there is. I go from wet at the top to dry at the bottom. The fastest movement of between wet and dry occurs as mud flows. Mud flows can be really rapid. What happens is the upper reaches of a alpine landscape get super saturated, and then they breach. Gravity overcomes and pulls that material down in a very, very quick event. We're talking minutes. All right. If we have a little bit of moisture in the landscape, the rock structure or the glacial till material can hold a lot of moisture over a long period of time, but at some point a failure will take place, and the failure itself happens really quick, matter of seconds. And then a rock fall doesn't require any moisture at all. What might happen here is you've got some ice wedging happening or salt wedging happening, and eventually after the salt or the ice is removed, the ice is no longer holding the piece that's going to fall to the rock face anymore. And once that ice is gone, the the rock ends up falling. So that's a classic example of a rock fall. There are other ways that rocks fall too, but that's the most common mechanism that creates rock falls. A medium speed rock movement of mass wasting is the flows. All right, so that's this right here, flows. So we've talked about falls, and we're going to talk about flows now. So a flow then is where it's similar to a landslide, where the rock gets saturated, but there's a lot of water in this condition, and the water continues to seep through the rock. And as it seeps through the rock itself or the debris flows down the side of the feature, down the side of the hill or down the side of the mountain. And it may move over a period of weeks. It might move over a period of years. A slump then, and here we've got what's called a rotational slump, and that's this shape right here, this convex lens, where we've got a piece of feature here, not very wet at all, just enough moisture where instead of it falling, it sort of rotates and slides. So there's pressure on the surface of the earth, and that pressure kind of starts with a slump, and then the slump just sort of rotates out from underneath, and it then sort of creates this stepwise pattern. Our last features, which are solifluction and creep, happen exceptionally slowly. Solifluction is the slow downward movement of material that happen with freeze-thaw cycles. And I've got a video that talks about freeze-thaw cycles. And so the soil becomes saturated in the fall, and the moisture in that soil then freezes in the wintertime, and in the springtime it unthaws and it flows downhill, and it takes matter with it. And it takes years and years and years for material here to maybe just move a couple of inches. On a rapid solifluction, it may take a decade to move a foot. Creep is the exact same process, this slow moving downhill, but it happens in the absence of moisture. Gravity is just slowly pulling the rock face on the surface downhill. And we've all seen where we've got fence posts, or in the diagram here, we've got power lines that are no longer perpendicular to the slope. They're creeping along at the same angle as the slope itself as they are pushed downhill. So that's the end of this slide set. I have another slide set for this week's lecture, so make sure that you look at that one as well.